Hi everyone, my name is Casey Silvernagel, and today we're going to discuss solving DDR memory challenges and how advanced simulation can help you discover potential issues in your designs. So why do you need a tool for analyzing DDR on your board? During a design process, the engineering team works to determine what component placement and routing is best, and what constraints they may need on elements of their design so that their end product works. This is important for many parts of a design, and DDR is no exception. In fact, often DDR failures are related to signal integrity issues in the design. When investigating potential signal integrity issues, designers may examine the four T's of the design. These are trace parameter, which refers to the width of the traces, trace impedance, and layer parameters that affect the trace impedance. Topology, how is the trace going to be run? Does it have a minimum or maximum length that it needs to be, or does it need to match the length of another trace? Technology, what are the effects of the driver edge rate on my design? Today, fast edges are not confined to specialized parts, and with today's devices, the edge rate, not the frequency of the signal, is what causes problems. And lastly, termination. These are decisions that engineering teams are already making today. To minimize issues such as crosstalk and noise, and to achieve correct timing for their design, engineering teams typically use their experience and rules of thumb to create constraints needed for their design. These constraints will need to go into the constraint management system and drive the PCB routing process. Engineers may also need to read design guidelines to see how to approach the design given the technology or application. Another method is to simulate. Simulation helps to ensure that the technology or application being used on a design will work right the first time. In addition to the basic signal integrity analysis, such as noise, crosstalk, and timing, we need to keep in mind the type of technology we are designing for. Today, we are focusing specifically on the DDR interface. When designing for DDR, there are another set of challenges that need to be considered, such as timing and voltage requirements. We have to make sure that the bits that are transmitted from the controller are received properly, and we also have to meet the timing and voltage requirements of the DRAM and controller. Also, there are several types of DDR which operate at multiple speeds. Typically, the faster the speed, the smaller timing and voltage margins are. Adding to the timing and voltage requirements of DDR, there are also features and capabilities of the DDR technology that come together to make it work, that need to be taken into account. ODT, or on-die termination. Terminations need to be different based on whether we're going to do a read or a write from the controller, and the terminations need to be toggled. This is important to the DDR analysis and need to be taken into account during simulation. Controller timing, which is the ability to change the setup and hold time for the controller timing. Flyby topology and write leveling for DDR3. In order to meet the DDR3 data rates, the address, command, and control lines do not go directly from the controller to each of the memories in a balanced length, but instead are daisy-chained using flyby routing. Flyby routing creates a timing skew between the address, command, and control and the data bits. This timing skew created in the DDR3 interface is corrected automatically by the controller using write leveling technology. Signal slew derating. This is the technique of adding or subtracting a delta time adjustment to the setup requirement of the DRAM. This can be very complex because each transition on each bit needs to be measured to determine the delta times, which can end up being thousands of measurements. With all of these different things to keep track of, how does someone go about managing DDR in their design? PADS can help. PADS Hyperlinks DDR has a convenient wizard-based interface that helps designers analyze DDR1, DDR2, and DDR3 designs. The DDR Wizard in PADS includes a default controller timing model, as well as the memory timing, which is provided by the JEDEC spec. Users can also modify the timing parameters based on the controller they will be using in their design. Also, for each technology that uses slew derating, measurements and calculations are performed automatically in the DDRX Wizard. Once the simulation is run, the tool creates an HTML report on the DDR interface that was being analyzed. This report includes information such as setup and hold times, as well as overshoot and undershoot, and which signals are non-monotonic, to give the user a comprehensive view of their memory interface. Let's take a look at PADS Hyperlink's DDR in action and see how it can help find potential issues in your DDR circuitry earlier in the design cycle. Starting in PADS layout, to access the PADS Hyperlink's DDR, we go to Tools, Analysis, DDR Analysis. From here, we can access the DDR Wizard by going to Simulate SI, run DDRX batch simulation. So the wizard initially opens to this welcome page, and this summarizes what the wizard allows you to specify. As the user walks through the wizard, there are detailed explanations of what each section is. This makes the wizard easy to use, even when using it for the first time. If the user or someone on their team has already run a simulation and saved their settings, here they can import their settings from a previous run, so they don't have to run through the wizard again. Otherwise, this page is used to tell the wizard what DDR interface we'll be simulating. This page is for specifying which device is the controller. And this page is for specifying the reference designators of the DRAM. Here we verify the IBIS models for the memory controller and DRAM. If they're not already assigned, we can use the Assign Component Models dialog box to assign those models. This page is where the user sets up which portions of their interface they would like to simulate. The next few pages are used to tell which controller signal connects to each DRAM. The tool can do this automatically if the user would like, by clicking the Perform Automatic Net Mapping. Notice once I clicked this that it filled in some of the information on this page. So clicking this will also affect the next couple pages. So here, you specify which nets are data strobes. They have already been assigned because we performed the automatic net mapping in the earlier step. Here you specify data and data mask nets and associate each net with the proper data strobe. Again, they've already been assigned because we performed the automatic net mapping. Here's where we specify clock nets. Again, they're already assigned. Here we specify address and command nets, and again, these have already been assigned as well. So here's where we set up control nets, and again, these have already been assigned. This section allows the user to disable nets if you want to run a quick simulation on a certain set of nets, not the entire DDR interface. This area is used to select which ODT models will be used. As you can see, these ODT models are pulled from the IBIS model. Here we verify the ODT behavior. And here is where we specify an IBIS model for the non-ODT signals. This section is for setting up timing models. We can use the generic JEDEC compliant models that come with PADS Hyperlink's DDR if we would like. If the technology that you're working with uses flyby routing, then this is the area where we can specify write leveling delays for byte lanes. Here's where we specify the stimulus for the simulations that we want to run. And here is where we set up additional simulation options for our simulation that we're about to run. And this is where the user sets up the parameters for the waveform quality checks. By default, the tool uses values from the JADEC specification. And here we choose how we want the tool to report the results of the simulation. We can save the waveforms to disk and make sure that it creates the HTML report for us. And here is where a user would save the setup data. This is for if you want to import at the beginning, where I had spoke about importing settings from a previous run. Now, before I simulate, I need to set up the ODT models that I didn't set up previously. So what I'll do is I'm just going to go to the beginning here, and I'm going to import one of these setup files. Now, what that has done is if I go back down to the ODT model area, you can see that it's defined the ODT models that I did not define as I was running through the wizard. So now that I've done that, I can run batch simulation. As you can see, when the simulation is done, it brings up the HTML report that we had asked it to create for us. It's got different tabs along the top that goes over the different sets of nets that we had simulated, and you can look through it and see how the different setup and hold times are. If I go to the differential nets area, we can see that this is color coded as well. So this differential net actually failed one of our waveform checks. And if you look, it's because it is non-monotonic. Depending upon the settings that the user gave when running through the wizard, the waveforms of the nets may have been saved off, and in this case, we saved it. So this would allow for the waveforms to be viewed in the waveform viewer for later. As you can see, PAD's Hyperlinks DDR is a very powerful tool that assists the user in setting up and running simulations on their DDR designs, and then gives the pertinent information about the nets simulated in an easy-to-read report. PAD's Hyperlinks DDR, which was just shown, is part of the PAD's product creation platform used by thousands of engineers worldwide to bring electronic product ideas to life. You may be aware that PADS has been delivering solutions for product creation for some time, and as part of the platform, we have a best-in-class schematic capture and layout. We also have component management, constraint management, DFMA, FPGA PCB optimization, signal integrity, and thermal analysis tools. We continually expand PAD's capabilities too, particularly in the analysis space that is so crucial to today's high-speed designs. Recent additions include electronic cooling, voltage drop analysis, DDR simulation, which I've showed you today, electronic design rule checking, and a new analog mixed signal environment, all of which are available at a minimal cost. The PAD's product creation platform enables the engineer to assess and make the appropriate design trade-offs. It addresses design complexity in multiple design consideration areas to help our customers get their designs right the first time. In this web seminar, I've shown you how you can use PADS to explore DDR circuitry to ensure proper placement, routing, and termination. I've also shown how PADS Hyperlinks DDR creates a nice report that makes it easy to see where a design may have failed to meet timing or voltage requirements. If you would like to learn more information about PADS or are interested in evaluating one of our new extensions to the PADS product creation platform, I encourage you to explore pads.com or contact a PADS reseller in your area. Thank you for attending the web seminar today.